In section 2.5, we look at the basics of how the periodic table is structured and also some of the origins of the periodic table. So when we first start studying chemistry, we see the periodic table everywhere, and that's really because it's just very useful. So how did we end up with the current version of the periodic table? Well, the story begins in the 18th and 19th century, that is the 17 and 1800s, when many new elements had been discovered. And it was recognized pretty quickly once we got to around about 50, 60 elements that simply memorizing the properties of all of the elements was becoming an overwhelming task, and we needed a way of organizing the elements that it made it easier to understand the variations in their properties. So the method that kind of took off, if you will, that led to the development of the current modern periodic table was that developed by the Russian chemist Dmitry Mendeleev. And in fact, in Eastern Europe, they don't call the periodic table, they call it Mendeleev's table. And what Mendeleev did was he organized the elements so that those that were most similar in terms of their physical and chemical properties were placed nearest to one another. Now, Mendeleev didn't realize, because he didn't know about the existence of subatomic particles, but what he was actually doing was organizing the elements in order of atomic number, or that is, in order of increasing number of protons in the nucleus. But what Mendeleev noticed was that after a series of elements, the properties would repeat. So, for example, he would go along for a little while and he would find an unreactive gas. And then immediately following that unreactive gas, there would be a very reactive metal. Then you'd go along for a little while and you'd find another unreactive gas, followed by another very reactive metal. So what would happen is, instead of having a long line of elements in order of increasing atomic number, he ended up with more of like a rectangle. Now, Mendeleev was very smart. He observed that sometimes the properties between known atoms would increase radically. And so he realized that this was where an element that had yet to be discovered needed to be placed. And he would go along and he would predict what the physical and chemical properties of these elements were. They should be intermediate between the two elements that are on either side of the space. And so then that motivated chemists to go out and try and find these elements, and Mendeleev was often proved correct with amazing accuracy. For example, Mendeleev said that there should be an element that sits near aluminum. He called it eka-aluminum. And 17 years after Mendeleev made his prediction, scientists discovered this missing element and they called it gallium. Now, if you look at the experimental properties of gallium and those predicted by Mendeleev, they're really, really close. So, for example, Mendeleev said that gallium should have a very low melting point. It turns out that gallium melts at 30 degrees Celsius, which is just a little bit below body temperature and a little bit above room temperature. So that means that if you hold gallium in your hand, it'll turn into a liquid. Mendeleev predicted that the density of gallium should be 5.9 grams per centimeter cube, and sure enough, that's exactly what folks found. And Mendeleev predicted that when gallium reacts with oxygen, it's going to react in a 2:3 ratio, so 2 galliums combining with 3 oxygens. And sure enough, when you react gallium with oxygen, that's the exact ratio that you observe. So Mendeleev was onto something. He was creating a tool that allowed us to organize elements in terms of their periodic properties, but he also created a tool that allowed us to search for missing elements, which is really cool. So because of Mendeleev's work, rather than memorizing the properties of all of the elements on the periodic table, we just need to know how the properties vary across the table. And you can see this really clearly when we look at how the phase of an element at room temperature varies across the periodic table. If I want to find a gas, I know that I should look to the far right of the periodic table. However, if I want to find a solid, I should look towards the left of the periodic table. You know, that's a really, really obvious trend. So yeah, it seems to be working, and this makes things a lot easier for us. So in the modern version of the periodic table, every element belongs to a group, which is a vertical column, and a period, which is a horizontal row. Now, the groups are normally labeled in two ways. They're labeled with regular Arabic numerals 1 through 18, and that's the sort of official naming scheme, if you will. This is the one recommended by the International Union of Pure and Applied Chemists. And then there's the traditional North American scheme where the groups are labeled with Roman numerals, and that Roman numerals are commonly followed by either an A or a B. So we tend to kind of just flip between the two systems depending on what is most convenient. But what's important for you now to recognize is that the groups with an A in their names, that is the ones that stick up above the main section of the periodic table in the middle, the ones that are highlighted in yellow there, they are called the representative elements, or sometimes they're called the main group elements. So those ones are the ones that we're going to be mostly focusing on in general chemistry. An important thing to recognize is that elements in the same group tend to have very similar properties. That is, I want to say that the properties vary less as we go up and down the periodic table than they do as we go across the periodic table left and right. Those groups that sit below the representative elements, they most commonly have a B in their group designation. They're called the transition elements. And then you'll see that there are two rows that sit beneath the periodic table. These are referred to as the inner transition elements, and they don't actually have a group number. The inner transition elements are called the inner transition elements because they actually are meant to go inside the transition elements, but we pull them out and put them underneath and then push the ends of the periodic table together so that we can create a periodic table that fits conveniently on an A4 page. There are 7 rows or periods in the periodic table which are labeled 1 through 7. And something to point out is that those inner transition elements comprise rows 6 and 7. So we label 1 through 7, and then we have to remember that 6 and 7 sit below the main body of the periodic table. As I mentioned previously, properties of elements vary more greatly as we move left and right than they do as we move down a group. Now, something to be mindful of is that the periods are not always labeled on every periodic table. The groups always are. And if you do label them, make sure you label them on the right-hand side, 1 through 7, then 6 and 7 again for the inner transition elements. I suggest labeling on the right-hand side because people put hydrogen in the weirdest of places. Sometimes they put it in group 1A. I've even seen it over in group 7A, and sometimes they put it in the middle of the periodic table. But the important thing is you don't want to accidentally mislabel and not end up with enough periods. So always label on the right-hand side, and that won't happen to you. So the periodic table is not only divided into groups and periods, which forms a kind of grid reference system, it's also divided into metals, non-metals, and semi-metals. And you should get used to this kind of system. Hopefully you can see that most of the elements on the periodic table are metals. So if you do need to guess as to whether something is a metal, a non-metal, or a semi-metal, always guess metal because the odds will be in your favor. So the metals sit on the left 2/3 of the periodic table, and then they're separated from the non-metals by what we call the semi-metals, or what are sometimes referred to as the metalloids. And then the non-metals make up hydrogen and the elements that are in the sort of top 1/3 right corner of the periodic table. So metals have distinguishing properties. All of them are solids at room temperature, except for mercury, which is a liquid. They're shiny, they have a characteristic, what we call metallic luster. They look like metals, at least when they are freshly cleaned and they haven't become oxidized and they haven't reacted with oxygen in any way. Metals are good conductors of both heat and electricity. So if you attempt to pass an electric current through a metal, it moves through slowly. It doesn't cause heating. When something is a poor conductor, if you try and pass electricity through it, it just tends to kind of get hot and burn. And we make things out of metal when we want them to conduct heat well. So we make things like frying pans and pots and other things out of metals because, well, they're good conductors of heat. Metals can be stretched into wires without breaking. You can stretch a metal really, really thin. This is technically called that being ductile. And metals can be molded and pressed and bent into complex shapes. That is, we say that they are malleable. So they're the opposite of being brittle. Some of the metals have trivial names for their group names. Group 1A is referred to as the alkali metals. That's because when you dissolve them in water, it gives the water the property of being alkali. We'll talk about what we mean by that later on in future general chemistry classes. And then group 2A is referred to as the alkaline earth metals because these metals are often found in earth that makes water alkaline. So the origin of those names is kind of not particularly important. Just remember 2A goes with 2 words, 1A goes with 1 word. Those 2 rows that sit beneath the periodic table are known as the inner transition metals. The ones that are in period 6 are often referred to as the lanthanides because they come after the element lanthanum. And then the ones that are in period 7, beginning with thorium, are known as the actinides because they come after the element actinium. Now, it's important to recognize that every element that is in period 7 is radioactive. So all of the elements that are in the actinides are radioactive. In fact, any element that is heavier than bismuth is radioactive. So you might be aware that radon is a radioactive gas that can accumulate in your basement if the surrounding mineralogy produces radon gas and you have to open windows and stuff in order to stop that from building up. As mentioned previously, the nonmetals are in the top right corner of the periodic table and also include hydrogen, which is placed in a variety of different positions depending on the designer of the periodic table, but most commonly I think it's placed in group 1A. So the nonmetals have different properties from the metals. If they are solids, they're dull rather than shiny, and they are brittle rather than malleable and ductile. So a good example of that would be iodine or carbon. Both of those guys are dull, brittle solids. They're not good conductors of heat and electricity. If you try to pass electricity through them, they just kind of get hot. They might even burst into flames or something. The electricity just doesn't move through them well. And they're not great things for conducting heat. In fact, they could be used as insulators. Most of the nonmetals are solids or gases. The only nonmetal that's a liquid is bromine. So those that are gases are probably pretty familiar to you. Nitrogen, oxygen, fluorine, chlorine, and then every element in group 8A, helium, neon, argon, krypton, xenon, and radium, radon, which we mentioned earlier. So only 2 liquids on the periodic table at room temperature, mercury and bromine are liquids. Most elements are solids, and then there's a handful of gases. So every member of 8A is a gas, so that makes that easy to remember. The members of group 8A are referred to as the noble gases because unless it's exceptional circumstances, they don't combine or interact with other members of the periodic table. An older term for these is the inert gases, and people still use that term. So helium, neon, argon, krypton, xenon, radon, either the noble gases or the inert gases, they're all gases, right? They're the snobs of the periodic table. They are the kings and queens of the periodic table. They don't mix with the other elements or combine with the other elements unless something unusual is happening. Group 6A is referred to as either the oxygen group or the chalcogens. And every member of group 6A is a solid with the exception of oxygen. Group 7A, beginning with fluorine, these guys are known as the halogens. Some people might call it the fluorine group, but almost always they call them the halogens. Fluorine and chlorine are gases. Bromine, as we mentioned earlier, is a liquid, and then iodine and astatine are solids. But I should point out that astatine is extraordinarily rare in our universe, so highly unlikely that you're ever going to see any astatine. Group 5A, which is the group that begins with nitrogen, and these guys are known as the pnictogens. And bismuth is in this group, and bismuth is the heaviest non-radioactive element. So everything after bismuth is radioactive. Okay, so just pointing that out here. These guys there, group 5A, are the pnictogens. Okay, the metalloids lie on a diagonal line that separates the metals from the nonmetals. These are highlighted in green here. And they have properties that are intermediate between metals and nonmetals. All of them are solids at room temperature. So perhaps familiar semi-metals to you would be silicon, or maybe even germanium and arsenic. So an example of their metallic-like properties is silicon is used as an electrical conductor in electronic devices, so silicon chips, and gallium and arsenic are also used in this manner as well. However, all of these guys are brittle solids, and being brittle is a non-metal characteristic. Okay, so let's look at some example problems from the book. So it says, using the periodic table, classify each of the following elements as a metal or a non-metal, and then further classify each as a main group or representative element, transition metal, or inner transition metal. So just making it clear, the two groups on the left and the 6 groups on the right that poke up above the middle section of the periodic table, these are the main group or representative elements. The elements that sit in the middle of the periodic table between the two sections of the representative elements, these are the transition metals. And then it's pretty easy. The guys that are underneath the main section of the periodic table, they're the inner transition metals. So the first thing I'm going to do is just find where these guys are located. So uranium is element 92. There it is there. Bromine, that's that liquid at room temperature. There it is over there. Strontium over on the far left. And then neon is in group 8A. It's what we call a noble gas. So we have to classify as a metal or a non-metal, and then either representative, transition, or inner transition. So for A, I hope you can see that uranium is in those inner, I don't know why I'm writing the name out. Uranium is in what we call the inner transition elements. So it is a metal because everything that is in the inner transition elements is a metal. So it's in the inner transition. So make sure you get both parts. Okay. Now, bromine up here, bromine, we'll put it up here, B for bromine. It is definitely a non-metal. It's over there on the far right of the periodic table, so it's a non-metal. And group 7A are part of the main group. So we're going to classify that as being in the main group. Okay, strontium over on the far left, it's a metal. In particular, it's an alkaline earth metal, but we're not asked to mention that. We just have to say that it is in the main group, or we could say that it's a representative element. And then last but not least is neon. All right, neon up here. And neon is in group 8A in those noble gases. It's a non-metal. It's on the very far right of the periodic table. And it is also in the main group, or the representative elements, however you want to phrase it. Okay, so we got all four of them, and it looks like OpenStax agrees with me. Okay, let's have a look at this one. It says use the periodic table to give the name and symbol of each of the following elements. Okay, we should find them, and then we'll write the name and symbol, which is really just a matter of copying it over from the periodic table. So it says the noble gas, so that means we're in group 8A, in the same period as germanium. So here's germanium. So what we're interested in is this guy here. So symbol and name. So the name is krypton, and the symbol is uppercase Kr. So the alkaline earth metals, so alkaline earths are in group 2A, in the same period as selenium. So selenium is just a couple of spaces over from germanium, so it's in period 4. So it must be this guy, which is calcium, and that has the symbol uppercase C, lowercase a. Next one is the halogen. So the halogens are group 7A or group 17 in the same period as lithium. So lithium's in period 2. So that halogen must be fluorine. So when you spell fluorine, it's slightly unintuitive. It's F-L-U-O-R-I-N-E. And so often people get the U and the O switched around. And it only has a one-letter symbol, so it's just uppercase F. Okay, so the chalcogen, so the chalcogens are the oxygen group, so group 6A or group 16 in the IUPAC method, in the same period as cadmium. So cadmium's in period 5, so that's gotta be tellurium, all right? So tellurium, and the symbol is Te. Don't confuse it with technetium. Okay, cool. So just take your time, and it normally works out just fine. And we got all of those correct. Okay, so that concludes the video introducing the periodic table.